Okay, so let's continue with the chapter 22. So here we will get something more difficult. So we will start to use some calculus to really find the E field generated by some specific structure. Even though those structures are relatively simple, okay, kind of there will be quite a lot of symmetry inside the structure, so that hand calculation is possible. Yeah. Okay, so here this case is electric field due to the line of charge. Okay, actually a ring. Okay, so actually for this one you don't necessarily need to use calculus, but this is like an example to get you familiar with how to apply calculus. Okay, so maybe this one you actually don't need the calculus at all. You just need some multiply. Okay, because calculus is like adding many small things together. Okay, so if you just integrate a constant, it will be just like adding many constant together, which is just like a multiplication. So actually for this one, that is the case. You don't actually need the calculus at all. But it's just an example to get you familiar with how to apply calculus. And then, so later on, when there are some cases there, you must use the calculus. Then you have some experience with this one. Okay, so actually, yeah. So here's the case. We have a ring. Okay, we have a ring. We assume this ring is very thin. Okay, we're thin. It's just like a line, okay, without any thickness. And then there are some charge. And then as much as this is a perfect circle, so the charge will be distributed uniformly on the surface, okay? Or actually on this line, okay? Or on this ring. So, so it says the equation for the E field set up by a particle does not apply to an extended object with charge. Okay, so previously we have E equals K times Q over R squared. So which is just apply. We can just be applied for a single charge. Okay, or multiple charge, and then you can use you can add up all the E field as a vector sum. But here, okay, so this is a continuous distribution. You cannot count or how many charge inside this structure. So we actually need to use the calculus to try to cut this ring, okay, cut this continuous charge distribution into infinite many discrete charge, okay, and then we try to add all these infinite small E field together. Okay, so so simply speaking, okay, so here it says to find the E field of an extended object at a point, we first consider the E field set up by a charge element, okay, a charge element, which means we try to cut this ring into many small parts, okay, extremely small parts, okay, although these look quite long, but it's just let you to able to see it, okay. So let's assume, okay, this ds is infinitely short, okay, infinitely short. Okay, and on this segment ds, we have a small amount of charge dq, okay. Of course, the whole charge on the ring will be small q, okay, the total charge on the ring. Okay, where the element is small enough for us to apply the equation. Okay, so as much as this is small enough, short enough, so we can consider this part is a single charge. So so where the okay, so then we can sum all the small elements together, and then so actually every element will generate dE. Okay, so every ds, okay. On this ds, we have dq, very small amount of charge, and then it will generate dE, okay, at the point we concerned. So finally, okay, so we try to consider all the small part on this ring, and then finally all the DE we add up together, so that it will be the total E field generated by the whole structure. Okay, so a ring of uniform positive charge, a differential element of the charge occupy the length ds, okay, ds with dq, okay, greatly exaggerate 是夸张的 ，okay， 让你看得清楚。Okay, so this element set up an E field D at point P. Okay, just as what I mentioned. So, so the second step. Okay, so the first step is to separate into many small segments so that we can consider it one by one. Okay, so the next step is to cancel some components. Okay, as much as it can be hand calculated. So there must be some symmetry so that you don't need to suffer a lot for the calculation. So and most of the case we can cancel one or two of the components. So for this case, it is like yeah. Let's consider. Okay, this is ds. This is ds, and we would like to find the DE on the point P. Okay, so here we try to cut this one. Okay, this is the cross section, something like here, and then you can consider. Okay, so this center of the ring will be no. This point P. Okay, this is the point P. Okay, the point P is actually here. Okay, so ds will generate the DE, okay, pointing to this top right direction, okay. We assume the charge is positive. So DE actually points to that side, okay. Just ignore this one first, okay. So you can consider this DE is generated by this ds, okay. So, and then we can see, okay, this is the z-axis, and then, of course, this will be, I don't know, can be called the x-axis, okay? This is x-axis, this is z-axis, okay? And then this is x-axis, this is z-axis, like this, okay? And then you can decompose this dE along the x and z-axis, so that so that it has this z-axis component and y and x-axis component. Okay, so yeah, so this is pretty much for this one. And then, as much as this is a perfect circle, you can always find the part that is symmetry to this part. Okay, so this part, okay, maybe we can call this one ds or ds prime, whatever you like. Or maybe I call it ds prime. So it will generate DE prime like that. Okay, so actually this is the DE prime. Okay, of course the textbook use DE because actually they have the same magnitude. So they just simply use DE, but I just want to emphasize that, okay, from this DE, ds prime, okay, it of course have a DQ prime or DQ or whatever you like, because the charge is distributed on the ring uniformly. Okay, so yeah, so as much as ds and ds prime is has the same length, so they have the same charge amount DQ there. Okay, so whatever. So actually for this ds prime, okay, it will generate DE prime, okay, like this. And then similar, we can just decompose it along the x-axis and z-axis. So the z-axis component, okay, so this one and this one points to the same direction, but for the x-axis component, this one and this one actually points to opposite direction, but with the same magnitude, so they cancel each other. Okay, they cancel each other. So the only remaining component is the z-axis component. We don't need to consider the E field along other axes. So this is the idea of canceling components. So after we find the small DE generated by the small DQ, then we will be able to find this DE along a certain direction, and then we try to decompose it along maybe like XYZ direction For this case, only two of the three directions. So actually, also there will be two components, or one is along the x-axis, one is along the z-axis, and then finally we can find that the x-axis component cancel each other. So only z-axis is important. So finally, we just add up the z-axis component because we know only z-axis component remains in this structure. Okay, so let's go to some more complicated math here. So actually, ds and then this is the angle theta. Okay, so this is also theta. Okay, and here we consider this part is z equals 0. So this part is z. Okay, this part is c. And then actually, okay, we would like to find the E field here, okay, generated by this ds. Okay, so the distance from this ds to the point P, okay, is important. So this is r, okay, this is r. Although that is not the known variable here, okay, the known variable will be z rather than r, yeah, because as much as you get the ring, we would like to find the E field along the z-axis, similar to the electric dipole, okay. The E field is the expression of the E field is elegant only on this z-axis or outside of the z-axis. I'm not sure whether the closed form solution exists. Okay, but anyway, so this one only find the E field along the z-axis. So z will be the known variable. R is not the known variable here. Okay, although this is a constant and z will be a constant for a specific case. So yeah, so never mind. So actually here we can see, okay, this is actually the theta. This is actually the theta. So the z-axis component will be like dE times cosine of theta, okay, dE times cosine of theta. So cosine of theta is what we want to know. So cosine of theta, okay, in this right angle triangle, so cosine of theta will be z over r. R will be this radius, okay. So of course the radius of the ring should be a known variable. So we would try to express r in terms of z and r. Okay, so according to Pythagorean theorem, so r will be the square root of c squared plus capital R squared. Okay, so here cosine of theta is expressed by z is a known variable, r is another known variable. So yeah, this is okay. And it's just try to express the square root as the power of 1/2. Okay, so nothing special here. Okay, so according to what we discussed in the previous page, we would like to find dE cosine of theta. So dE cosine of theta here. So dE will be like this one k times q. Okay, you ask q, it should be q or dq. Okay, this one it should have the amount of a dq. Okay, but if we just write dq here, we don't know how to integrate. Yeah, because we would like to integrate along the circle. Okay, so dq, okay, we don't know how to integrate. So we'll try to express dq in terms of ds, okay? And then, okay, here comes with another variable, lambda. What is lambda? Lambda is defined as the line charge density, okay? 线电荷密度 okay, 线电荷密度 so which means that within a unit length, within 1 meter, how many charge are on a meter. Okay, so this is a linear charge density, yeah, because this is a very thin ring, okay, so it only have one dimension, okay, one dimension, which is a linear charge density. So the SI unit will be like coulomb per meter only. Okay, later on we will also have a surface density which will be C over m squared. Okay, but for the next case. Okay, so here we will have dq. dq is actually lambda times ds. Okay, so the charge will be the charge density multiplied by the length. Okay, ds is the length. ds is the length multiplied by the linear charge density will be the charge amount on this ds. Yeah. Okay, so hopefully makes sense. And then over r square. Okay, r square is this one. Okay, so this term is more or less the dE. Okay, and then for the cosine part, okay, this is the dE, and then for the cosine part is here. Okay, which is actually this one. Okay, so nothing special. And also we would hope to express this r in terms of square root of c square plus r square, square root of c square plus capital R square. So all together, this one becomes this one, okay, with the square, which would be like c square plus r square, and then multiplied by this one. All together will be 3 over 2 power, okay, here. And okay, so dE cosine of theta will be like this one, move it down, and then z go down here, lambda go down here, ds go down here, and then these two become c squared plus capital R squared to the 3 over 2 power. Okay, so this is pretty much the dE cosine of theta, and then we will be able to integrate it. Actually, this is so this whole term is independent to ds, so which line we are integrating a constant. So you may consider, okay, we don't necessarily need the calculus, but just as what I mentioned, this is just to let you familiar with how the whole process. Okay, if for some case we really need calculus, then this is an easy example for you. Okay, so this is the expression we will be ready for integration. Okay, so the final step will be integration or integrating the small amount of dE. Okay, so E will be like integration of dE, which will be integration of dE cosine theta. Okay, what I mean is E will be integration of dE, okay, something like this, okay. But according to what we derive in the previous pages, okay, we already know that, okay, we only consider the z-axis component. Only z-axis component remains, okay, which will be dE times cosine theta, and then we don't use the fractal notation here. Okay, so in that case, we just put this expression here. Okay, put that expression here. And then we would like to integrate ds, okay, for the whole circle, which will be from 0 to 2 pi r, which will be the circumference of a circle. So yeah, so this is the lower and upper bound for the ds. And then, as I mentioned, okay, none of these things, okay, all of these things are constant for this integration, and none of them are related to ds or independent to ds. So which means that we are like integrating a constant, just like when you learn calculus. If you have something like integrating 3 dx from 0 to 4, okay, which will be easy, which will be like 3 times 4, which is 12. Okay, then this is it. Okay, we don't know what is integration. So this is a similar thing. we can just put this whole thing in the front. Okay, so integrating this ds from 0 to 2 pi r, which is nothing but 2 pi r. Okay, and then this whole stuff is this one. This whole stuff is actually this one. Okay, and then this integration goes to here. Okay, so finally we just need to do some cancellation. So finally, lambda times 2 pi r, will be the total charge. Yeah, because we assume the charge density is lambda, and then the charge density is uniform along the whole ring. So the length of the ring, which will be, or the circumference of the circle, is 2 pi r times the lambda will be the total charge amount on this ring. So this is pretty much like this. Okay, so we will replace lambda 2 pi r as q. All the others remain the same. So this is actually the final expression. E equals k. This is k times qz over z squared plus r squared to the 3 over 2 power. Okay, so this is the general solution for the E field along the z-axis. Yeah, but here we also consider the far field condition. Yeah, for this far field condition, we assume z is much larger than r. Okay, I'm not sure whether you know this notation very well. Okay, this is much larger than, 就远大于 much larger than. Okay, so z is much larger than r. Okay, so last time which is like r over z will be 0 or tends to 0. Okay, whatever you want to say. Okay, so something like that. Because as an engineering student, we usually try to do some approximation as much as the answer is relatively accurate and will be accepted. Okay, we don't need a very accurate solution or exact solution. Yeah, because for engineering, you can have all the things accurate. Okay, let's say the Q or the length. Okay, you can never get it 100% accurate. There must be some error. Okay, so as much as the error is acceptable, then it will be fine. Okay, so here what we assume is the far field condition, which means that, okay, we consider a point which is quite far away from this ring. Okay, which is quite far away from this ring. Okay, which means that this distance, okay, this distance z is quite larger than the radius of the ring. Okay, so in that case, if we have a z is much larger than r, so within this one, as much as z is much larger than r, then it will be tends to c square only. Okay, c square only. Okay, because one is much larger than the other one. Okay, so when you add them together, then the r will be like very small, and then you can discard it. Just imagine, let's say this is 10, okay? This is 1, okay? So after you add them together, it's 101, okay? Which is approximately 100, okay? So we just get rid of it. Okay, so finally, c squared to the 3 over 2 power will become c cubed, and then cancel with this z will become c squared here. Okay, so finally come up with a very elegant, a very familiar expression here. So the idea is like, if you are very far away from this ring, the E field generated by it will be look like all the charge concentrate on the center. Somehow similar to the shell theorem we mentioned in chapter 21. Yeah, so this is pretty much it. Okay, so far any questions? 有没有问题？有冇問題？係。你说是哪一个？第一个吧。哦。 Okay, so I assume is D E 这里吗？这里吗？对对对 ，OK。Yeah, so D E, okay. Okay, so yeah, so there will be two parts. Okay, so of course cosine of theta is actually this one. I suppose you should be able to know that, right? Okay, for the DE originally previously will be like E equals K. Okay, so 1 over 4 pi epsilon I just write as K times Q over R squared. Okay, originally the expression is like that. But here in this case, it will be generated by the small amount of dq on the ds. Okay, so the expression, we will rewrite it as something like this. dE will be k times dq over r squared. Okay, we just consider, okay, this dq is along this very short distance ds. Okay, and then as much as this ds is very short, we consider it is somehow like a point charge. So we can actually use dq here. Okay, so as much as this dq, okay, the d you just ignore it. Okay, you just consider dq is a variable. Okay, and then it will generate another de. Okay, although you have learned the calculus, you know, oh, d is some evil things, but actually you just consider dq de is just are just two variables. Okay, so this dq is a point charge. Okay, so and then we consider the E field DE generated by this ds, and the distance is small r. So this expression is okay. Okay, so k is a constant, and then r is the distance between them. So we only have dq here. dq over r squared times k will be the de. Okay, the de is generated by this dq. And then how do we go to here? Okay, so the only different thing is that, okay, this is still k, this is still r squared. So the only different thing is this dq equals lambda ds. Okay, so why do we need to make this change of variable? Yeah, because the idea is like we would like to integrate. If we just remain dq there, we don't know how to write the lower and upper bound, right? Okay, so the idea is like, because we would like to integrate along the circle, so the lower and upper bound will be possibly from 0 to 2 pi r, okay, something like that. So in that case, we would like to change this dq in terms of ds, but dq and ds is not the same thing. Okay, dq is the charge, ds is the length. So we must introduce the linear charge density here, 现电荷密度. Okay, so that dq is equal to lambda ds. Okay, but all of them, yeah, so lambda will be just a constant. It will be just like just appear there and then finally absorbed it. Okay, so here we have this dq equals lambda ds, which is only considered a small part. And then at the end, at the very end, we know the total charge amount is q. Okay, so finally we get q equals also lambda times 2 pi r. Okay, so this part we only consider the small length ds. Okay, but this part we consider the whole ring. Okay, at least the charge density is uniform along the ring. Okay, so that we can use the multiplication. The density multiplied by the length will be the total charge amount on the ring. Okay, so finally we just absorb this lambda 2 pi r as q here. Okay, something like this. Well, okay, so far still any questions? Okay, if not, we move on. So, Let's take too much time to do. Okay, so so let me finish this sample problem, yeah, because it is quite similar to the case we discussed. Okay. Yeah. So here it says a plastic wad having a uniform distributed charge negative Q, negative capital Q. The rod has been bent in 120-degree circular arc. 就是变成一个120度的圆弧啊。Okay, so something like this. Okay, starting from here to there. Okay, so with a radius small r, replace coordinate axis such that the axis of symmetry of the rod lie along the x-axis. Okay, so 这个是对称轴 symmetry of the rod. Okay, so that will be 60 degree on the top and then 60 degree at the bottom. Okay, the origin at the center of the curvature P of the rod. Okay, so P is the center. So in terms of Q, capital Q and small r, what is the electric field E to the rod upon P? Okay, so we would like to find the E field at this point. Okay, so let's us consider. Okay, so this is ds. Okay, and then the charge is negative. Okay, the charge is negative. So the dE will be start from this point towards this ds. Okay, so this is dE generated by this ds, right? And then this is x-axis, this is y-axis. Okay, this is y-axis. So we would like to decompose it, this dE along x-axis and y-axis. So like dEy and then dEx. And then as much as this circular arc is symmetry to x-axis, we can always find this ds prime. Okay, this part and this part are always proportional to symmetrical to each other. Okay, for other ds, okay, let's say for this ds1, and then you can also find ds1 prime. Okay, also. So even though you go through the whole arc, okay, or maybe you go through half of the arc, you can always find is a symmetrical part. Okay, okay. So for this ds prime, okay, it also generates dE prime or dE, okay, in this direction. Okay, pointing to the bottom right, Okay, so you also decompose this dE or actually dE prime. Okay, actually dE prime, okay, generated by this ds prime. Okay, so we have this y-axis component, this x-axis component. So you can clearly see that, okay, this one and this one, okay, actually points to opposite direction, but with the same magnitude, so they cancel each other. So we only consider the x-axis component in this case. Okay, so we can say that dEy cancelled. Okay, so only dex assumed. Okay, so we consider dE will be like k times. Okay, we also consider the linear charge density is lambda. Okay, so lambda ds will be dq in this case. Okay, lambda ds over the radius is small r. Okay, the radius is small r here. R squared. Okay, so this is dE. Okay, so dEx will be dE times. Let me see. So we possibly, because this is a xy coordinate, okay, as a polar coordinate, we will always define, this is 0 degree. So this is the theta, and cosine of theta. Okay, so this is this one dEx. Okay, will be dE cosine of theta. So dE also cosine of theta. So this case, which will be k times lambda ds. Lambda ds over r square. Okay, which will be the front part and maybe I use another color, the green color. Cosine of theta will be what? Okay, we just remain it. Okay, so just leave it there. And for this case, okay, even though ds is not integratable, okay, because we have another variable theta. Okay, we have another variable theta, so we need to introduce the polar coordinate. Okay, for the polar coordinate, we have something like this. Okay, for the polar coordinate, it will be like, okay, suppose this is r, this is theta. Okay, so let me see, d theta. Okay, so d theta will be like this. Okay, suppose this theta is increased by a small amount of d theta, so this length, okay, this length will be ds. Okay, this length will be ds, will be r times d theta. Okay, so the arc length will be like the radius multiplied by the angle in radian. Okay, 对，就是这样，就是这样。Okay, so here we have this expression for the polar coordinate. Polar 极坐标 polar coordinate polar coordinate 极坐标。Okay, so we have ds equals r d theta, so it becomes k times lambda r d theta, and then over r squared, and then cosine of theta. Okay, like this. Okay, you can consider this one. This one is ds. Okay, so it becomes r d theta here. Okay, like this. And then we can actually cancel this out with this r squared partially. So finally, we would like to integrate this dex along this length L. Okay, this rod L. Okay, so it will be like, we put this expression here, which will be k times lambda cosine of theta over r d theta. Okay, we just rearrange it because they are multiplied together. So rearrange the order doesn't change anything. Okay, so here we need to consider the lower and upper bound. Okay, so this is from negative 60 degree to positive 60 degree. Okay, so in radian will be negative pi over 3 to pi over 3. Yeah. Okay, so most of the stuff are constant. K, lambda, r are all constant. So we actually only integrate cosine of theta d theta from negative pi over 3 to pi over 3. Okay, so integrating cosine of theta is simple, which is nothing but sine of theta. So we have a k times lambda over r. And then sine of theta evaluate from negative pi over 3 to pi over 3. So sine of pi over 3 is square root of 3 over 2. And then this is negative square root of 3 over 2. So after subtracting them, so it becomes a square root of 3. Yeah. So finally, it becomes square root of 3 k lambda over r, something like this. Okay, finally, okay, this is lambda. This lambda is what we introduced. We need to eliminate it because we would like to express it as q. Okay, express it as q. So we need to find the expression. Okay, q will be like r times the angle. Okay, this is 120 degree, which is 2 pi over 3. Okay, so this is the angle multiplied by the radius, and then multiplied by the lambda. Okay, so this is the arc length. Okay, this is the length of the rod. Okay, r times 2 pi over 3. Okay, this is the length of the rod. This is the linear charge density. Okay, so this lambda times the total length will be the total charge. Okay, yeah, because we already consider the direction of the E field, so we just ignore the negative sign here. Okay, so finally we can get lambda. Okay, so by moving this part to the left side, we get lambda equals 3q over 2 pi r. Okay, so we try to put this expression to there, okay, to eliminate the lambda. Okay, so finally we will get 0.83 kq over r squared. Okay, so this is the final answer. Okay, so any questions?